Alright, so welcome once again. This time we are coming to talk about capacitance and dielectrics. Okay, so when we are talking about capacitance, it's actually the ratio of the charge and the voltage, which is the capacitance is equal to the charge divided by the voltage. Okay, so mathematically, C is equal to Q over V. Okay, but from our previous lesson, we've learned that electric field is equal to what? The charge divided by the permittivity naught times what? Area. And that same electric field is equal to what? Your voltage times what? D. So from here, we can equate these two. Okay, you can equate these two, giving us Q over E naught A is equal to V over D. From there, we will make V the subject. Okay, so if we make V the subject, then we come and substitute this formula for V into this first equation. Okay, so if you substitute it into it, you realize that what? The charges cancel out, the Q cancel out. Okay, so from here we can draw a conclusion that capacitance does not depend on what? On the charge. So this is the main reason why capacitance does not depend on the charge. Though from this formula you could see that C is equal to Q over V. In turn, capacitor does not depend on the charge. Capacitor depends on only the area, the permittivity in the and the distance of separation. So for that matter, we consider capacitance as a geometric property. Okay. So let's look at something. Let's look at this one. Let's look at this diagram. This is the plate of the capacitor, surely to have an area. Okay. And this is the distance of separation between it. If there is nothing here, this means that we are considering it as what? As air. For that matter, if it is air, our E is equal to E naught. For that, and if the dielectric here is a vacuum or air, we consider the K to be equal to 1. That's why normally we see our capacitance, the formula for capacitance to be equal to what? E naught over A divided by D. Rather the K, rather for us to not bring the K. If we are using this formula, then this means that what? The space between the plate is what? A vacuum or air. So let's consider putting a dielectric inside. The moment we put a dielectric inside, you see, if you are taking this one as a distance and we are inserting a dielectric inside, if you are inserting a dielectric inside, it actually increases the capacitance of the capacitor. Okay, it increases the capacitance of the capacitor. And if from here, if you are increasing the capacitance of the capacitor, this means that what? The voltage will surely drop. So there will be a voltage drop. So inserting a dielectric slab into the plate of a capacitor will increase the capacitance and it will decrease the voltage. And if you are decreasing the voltage, you are also decreasing the electric field. Okay, so that should be one of the things that you should keep in mind. Because from this formula, if you make V the subject, V is equal to ED. So if you increase E, you are going to increase what? The V. The same thing applies here, that as the voltage decreases, then our electric field will also what? Decrease. Okay, so now let's look at the relationship between the energy and the capacitance. As if already stated earlier, this is our energy stored in the capacitor, and we can assign it with this formula, that E is equal to what? Q squared all over 2C. Okay, but from our previous formula that C is equal to Q over V, then we can make what? Q the subject. And if you are making, alright, so this is our energy that is stored in the capacitor. So from here, if you are putting Q over V into this equation, then automatically it will turn to the reciprocal of it. And we are going to have what? Q squared all over 2 times V over Q rather. Okay, and at the end, we are going to have this Q and one of the Q's here will cancel out, giving you only one Q here. So our E, another formula for what? Energy stored in the capacitor is equal to what? QV all over 2, or half QV. Okay, so this is the relationship between it. And from here, you could see that the capacitance depends on the what? On the energy stored. Okay, so if you are inserting a dielectric slab into the plate of a capacitor, if you are inserting it into it, this means that you are increasing the capacitance, and as you increase the capacitance, automatically you are decreasing the electric or the energy stored in the capacitor. Okay, so that's the relationship between it. So from there, now let's look at another thing from here. So we can also generate another formula that E is equal to CV squared all over 2 from here. our C is equal to Q over V. Then we can make Q the subject. If you are making Q the subject, then our Q is equal to what? The capacitance times the voltage. Okay. Then from there, our E is equal to QV. We will make what? CV the subject. As you can see CV here, E is equal to QV. So wherever we see Q, we put CV there. So CV times another V, which will give you what? V square. Then your C here divided by 2. Okay, so that's the main idea behind what capacitance and dielectrics. In case maybe you are asked questions that are very qualitative and it doesn't involve any calculation, these are the basic knowledges that you should know and keep it in mind, and that will help you answer most of the questions. Now, let's consider another example, or let's consider another part of what? Our electricity. So here, you are saying that charges through different diameters of wire. Okay, the material used for the wire is the same, but just that they are having different diameters. If you are saying that a wire has a large diameter, then this means that what? It is having a larger area because the diameter is directly proportional to the area. Okay, and if it's having a smaller diameter, then it's the inverse of it, or vice versa. Okay, so let's consider this one. This is a wire. You could see that this one is bigger. The surface area or the area of the wire is bigger as compared to this one. Then automatically this one is having a higher diameter than this one, or a larger diameter than this one. But there's one thing you should keep in mind. Regardless of the diameter, if you are considering the current, the amount of current that is passing through the wire, it is the same like the initial current that is passing through this wire with a large diameter will be the same as the one that is passing through this one. So the passage of current through a wire or a connecting wire does not actually depend on the diameter. But when we are talking about a velocity drift, for instance, let's say you are having electrons. They are moving from here. You are having electrons which is moving in this area of the wire. It is moving to the smaller diameter of the wire. Okay, you could also relate it to pressure. If there is the area, you see how this one is moving, it will get enough spaces for it to move freely. Okay, but the moment it gets to this side and it is moving to another wire which is having a smaller diameter, you could see that the electrons will increase, the speed of the electrons will increase, and that's what we call a velocity drift. Okay, we are saying that the velocity drift will increase because as electrons move from this side to this side, there is a constriction here. Okay, so the movement of the electrons will be faster as it enters the smaller one. That's why we are having our I. So here we can see directly that the diameter and area are not the same. When the current moves from the larger diameter to a smaller area, the velocity drift increases. Okay, as far as we are having difference in diameter of the wire, there will be a change in velocity drift. It's either it's going to increase or it will decrease. If it is increasing, then if the velocity drift is increasing, then this means that it is moving from a wire of a larger diameter to a wire of a smaller diameter. That's why the velocity drift is increasing. Okay, so that's a fact that you should also know about it. For the current that is passing through, they will be the same, but for the electron or for the velocity drift of the electrons through the two wires made of the same material but different diameters, they are not going to be the same. It's like a pressure. When we are having a smaller area, the pressure will increase. Okay, so the pressure here will increase, which will cause the electrons to also move faster as compared to the one that is here with a larger area. From here, the electrons moves freely, and it won't be as that fast as the one that is passing through the wire with the smaller diameter. Okay, so now let's consider this fact. Again, there's another thing that you should also know. Here is our potential energy. Okay, this is our potential energy. So as the electrons passes through the resistor, the PE decreases as it passes through the resistor. So all they are trying to say is that we are having our potential energy to be this side, and we are having another potential energy to be this side. You can consider this one to be current that is passing through. The moment there is a current that passes through a resistor, the function of the resistor is to oppose the flow of electric current. And if the electric current that is passing through is being decreased, then automatically you should consider that what the potential energy will also decrease. So this is that the potential energy that is what that this electron is moving with before it enters the what the resistor will be what will be greater than the one, or will be greater than the potential energy of the electron that will be what that will move out of the resistor, because there is something that has gone on here, and this resistor is not going to what increase the speed, it's rather going to slow down. It opposes the flow of what electric current through a circuit. That's the main function of a resistor. For that matter, when you're having something like this, you should always keep in mind that as potential energy of an electron enters the resistor, it's going to decrease after it moves out of the resistor. Okay, so here our P final will be smaller than what our P naught. Okay, so that's the main idea about it. Similarly, it is also opposite to the EMF. If you're having an electron here and it enters an EMF acts as a pump. Okay, so one thing or one assumption that you can keep in mind that will make you understand things very well is that you just consider the EMF to be a pump. Okay, and here we are having a pump that pumps electron or something. Definitely there will be electrons here, but after it has pumped the electrons, all of them will be used up, and the electrons that will be returning back to the EMF. Let's say these electrons have moved to all the various circuits. We were having resistors, we were having a whole lot of things, okay, and these electrons have been able to manage to move through all the circuits, and it is back. Before it will reach here, the potential energy will be very small, but the moment it enters the EMF again, the EMF what gives it the same energy again, it pumps it out of it. So the potential energy that it will be using to move out of what the EMF will be greater than the initial one. Okay, so that's the main thing that you should keep in mind that will make you understand things very well. Okay, so this is the main idea about it. Here, when you're having a resistor, the potential energy of the electron entering will be greater than the potential energy of the electrons what moving out. And here it is the opposite of it. Because it is entering the EMF acts as a pump, which gives it the same energy that it used when it was moving through the circuit. Okay, so this is the main idea about it. Then now, let's move to here now, let's move to the potential energy. So when I'm talking about potential energy, the potential energy is actually what? The formula is what? Q1 and the test charge. It can be test charge or it can be another charge too, divided by the what? By their separation. So when you are having a charge here, which is Q1, and you are having another, or you are having a test charge, which is Q2 here. Okay. At this point, the distance between them is their separation, which is the R. Okay. So now, you see, here we know the distance between it to be R. The R can be any value at all. Now, you are seeing that from potential energy formula, we can derive the formula for work done. Work done is simply what? The negative change in what? Potential energy. Okay, and this is the formula for what? Potential energy. Change in potential energy. This is the formula. But they are saying negative change, so it's what? Negative, then your change in potential energy. When you simplify this thing, you are going to get what? U1 minus U2, or negative U2 plus U1. You are still going to get the same thing. Okay, so here now let's consider some things. Let's consider some things here. So let's consider the charge. If you are considering that the charge is brought from infinity to a point, the moment you are moving a test charge, or you are moving a charge from one point to another point of known, this means that what? You are doing a work is done. Work is done when you always move what? A test charge or a charge from one point to another point. But let's consider this first case where we are having what? A charge, but this charge is what? Is at infinity, and it has brought to a point, let's say A. Okay, we already know that. We already know the formula for work done, that our work done is equal to what? Negative change in what? Potential energy. You know the formula. So if initially it was at what? Infinity. If initially it was at infinity, and you can, from this formula, you can also see something here. You can just make your analysis here that if something is at infinity, let's say the distance is at infinity, then this is what? The value is very, 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 very large. Okay, and here, if you are having the value to be very large, if you are having R to be very, very, very large, then you are going to get something that will give you what? 0, or it will. So here, assume you are using limit, the limit will be approaching 0. It will automatically give you 0 on your calculator. Let's say you are having a very large number divided by this small number, you are going to get 0. Okay, so if you are moving a test charge, or if you are moving a charge from infinity to a point, then you should consider that what the first potential energy was at 0. Like how I've already explained here, that if the R is very large, the separation is very, very large. Okay. So you are going to get 0. So our P1 is 0, or our U1 is 0. Now it has been brought. Now you brought the charge. Okay, you brought the charge to what? To a point of a known value, where the R is known, but the R is not very big. The R is not infinite. Okay, the R is not infinite. So you know the value of R. Then from there, our P2 will be equal to what? Q1. Then our test charge divided by what? Our R. Okay, then from there, our work done is equal to what? As I said earlier, we already know that the formula is that our work done is equal to what? P, or the initial potential energy minus what? The final potential energy. And if you're having your initial potential energy to be 0 minus the final potential energy. So from here, we can always assume that what? Our potential energy is what? 0. Or no, we can always assume that if we are moving the test charge from infinity, then our first potential energy will be 0. And in total, the work done, if you are calculating for the work done, in total, we are going to get what? The energy to be what? Negative. Okay, so always put in mind, you are going to get the energy to be what? Or the work done to be negative, provided we are moving it from what? From a point, which is at infinity, to a point of a known value. You are going to get what? Negative. Okay, so for this particular case, for instance, the work done is always what? Negative. Yeah, there's a mistake here. So the work done is always what? Negative. That's what you should keep in mind. The work done is always what? Negative, which is, okay, the work done is always negative. Now, let me explain something small to you. When we are also having the charge, to be at one point, let's say here, let's look at this one. Let's say that the test charge is not at infinity. The distance between it is not at infinity. Let's say we are having A, or we are having point A. Okay, let's say the distance between it is A. It's not at infinity. Then this is that we are not going to get what? P1 to be equal to 0. P1 will not be equal to 0. P2 rather, P1 will be equal to what? P1 will give you a value. P2 also give you a value. So you just have to use what? Your formula that work done is equal to negative change in potential energy to get your answer straightforward. Okay, so this formula only works. Work done is equal to negative change in work done is equal to negative change in what? Potential energy. But when you are moving the charge from infinity, then our work done will be equal to what? Negative what? Potential energy of the second one. So it's not always that this one works. This formula will always work when you are moving the test charge from infinity to a point. Okay, and also when you are moving a charge from a point to infinity, then you are going to get a positive value. Okay, keep it in mind. When you are moving a test charge or a charge from a point to infinity, then you are going to get 0. This time around, it will become what? It will become the opposite of it. Let's say this one will be the first potential energy. But what I'm saying, this one will be the first potential energy. And if this one is the first potential energy, you know your value for your R. Initially it was at this point, and now you are moving the charge towards a very far place, which is called infinity. Then you are going to get 0. So it means that our change in potential energy, our P1 will rather be equal to what? A value, and our P2 will give you what? 0. So from there you are going to get what? Your solution to be positive. So it's not always that you are getting what? Your potential energy to be a negative answer. The potential energy too can be what? A positive answer, depending on the movement of the charge, whether you are moving it towards it or you are moving it away. If you are moving it away, put it in mind that you are going to get what? Negative. If you are moving it away, you are going to get positive, and if you are moving it towards it, you are going to get negative. So that's the main idea about it that you should keep. I'll later update you on a video about the dipole moment and the direction of the forces when you are having a test charge in between a dipole moment or something. Okay, so if you know that this video have been very helpful to you, or you just learned something new from this video, don't forget to like and subscribe. Okay, thank you.